equations like the color.
Oh, the color.
Filled up with black and
Yeah.
Oh, no, they might be. It might be. That was mine.
Yeah, they probably changed.
Okay, yeah, I think that's true. You got the data working?
Yeah. Yeah, hopefully. I'm Michael Giardino. This is Brandon Samuels, and our project was traffic monitoring using video sequences. And in order to identify vehicles, there's 5 steps to the basic image processing, and we have to create a background image, find the difference between the current frame and the background image, threshold and enhance the image a little bit, do edge detection, and then use the coordinates of the edge detection to find the centers. And this is what we had done in the previous our previous presentation, but I'm going to go over it rather quickly. In order to create the background image, we have to use a median of a sequence of images in order to remove the cars, because we expect that the vehicles won't be in the same position for more than, so we're using a 10-image sequence, so we expect that the vehicles won't be in the same place, over the entire 10 frames, so we can get a background image pretty efficiently. And it's just the median of a sequence of 10 images. Let's see. So here's our. Actually, can't see it very well. But this is an image of out of engineering building without. This was taken from 10 images, and you'll see the video later. But there are no cars driving here. But over the time, there were as many as 15 cars all through here.
What is that time?
I'm sorry?
What is that time, Jerry?
Let me see. Judging by the sun, I don't really remember actually.
I mean, the time period for your 10.
Oh, I'm sorry. It's I think it was 15 frames per second video, and it was every 3rd frame. So what's that? 3 seconds maybe, something like that. 2 or 3 seconds. And it wasn't the busiest time of the day either. It was more towards the afternoon. There's the idea we got from some previous work. So what they did is they did a weighted average. So we'd take our we'd calculate the median, and then we'd add a weight to a new frame every 100 frames, and we gave it a weight of 0.1. But our improvement to this was to, instead of just using a single frame and adding a weight to it, we were creating a new median each time. So because if there happened to be a car, especially a dark car, in our new frame, right here, see, because actually this right here is a car that was parked there for a while. So if you have a really dark car that and you just add the frame, a lightly weighted copy of the frame to it, you may get some dark spots which show up as noise. So by using a median a second time, a weighted median to add, we've reduced a lot of the false positives. So in order to get the vehicles, you subtract a frame each frame from the ground image, and you get something. You really can't see much of anything, but you see these. I wonder if we can. Do you think we can hit the lights, or is it too loud? Anyway,
I think I can see.
yeah, there's a vehicle there and some vehicles in the background. So then we have to enhance it a little bit. So we blur it just using a Gaussian noise, and you can't really see much of a difference. I think I have them side by side. Never mind. And that'll get rid of some of the noise that when we threshold it, you'll have specks. So in order to do that, we blur out the noise, and then we threshold it, and that gives you. There's a person, there's a car with the shadow, and then multiple vehicles in the background. And then we erode it and dilate it to get rid of some of these smaller specks. Thank you. Thank you very much. And let me go back then, just so you can see what the thresholded image looks like. This is it. This is it before, and then here's once it's been blurred, and you get rid of. You still can't see like really well, but there was noise and it's been blurred out here. And then it's thresholded to a binary image. and then eroded and dilated to kind of get rid of some of the multiple, if a vehicle is broken up into two pieces, it'll put it back together. And then we use edge detection and edge detection filter, and that gives you and this is what we use to calculate the area in the later part. It identifies the centers, and this is an actual tracking. This is just the centers of vehicles from the ground image, and then what Brandon worked on was actually tracking individual vehicles. So I'm gonna pass it off to him in a second, but this is the frequency of the vehicles that go by, and this was used in order to determine his correlation mask window. But we just used an accumulator. So every time a vehicle would go by, a vehicle where it was in the picture, it would add to the accumulator, and it was divided by the maximum frequency. And we can use this for prediction and tracking. And the next one is the size, because we use this as well. These are larger vehicles inside, and then this is smaller. As you can see, when it comes behind the trees, they get very, very small. And here, when it gets behind this tree, it's small as well. And this is the average size, where you take the frequency and divide it. You take the size and divide it by the frequency, and you can see here that the average size of the vehicles that go through is pretty much what you'd expect. It starts dark here. It starts large here, and then they get smaller as they go to the back. And then this is, in order to create his filtering, we have to make an estimation of what the size of the vehicle will be throughout the entire image. So this is just I'll hand it off to you, Brandon.
Okay. Okay, for my tracking algorithm, for it to work initially, we need a mask. We need something to actually look for. So pretty much we use Michael's method of locating the center of a vehicle. We pick one to test just the track, and we take that, we locate the center of that vehicle, and we use it as our mask to look for the next position. So we set that, as you see, we set the initial starting point as where we found the first vehicle, and we look in that area around the vehicle first. Depending on this previous array here, we use this to determine the size of our mask, the size of how big we expect the vehicle to be, pretty much. Okay, and then we set the mask size to 4 times the size at that point, and we begin to search. Okay. The searching method, it takes the mask and it creates a window around the spot where the vehicle is located, and we correlate that mask around the next image. So we take that mask and we correlate it across the image and try to locate the vehicle on the next image. Okay, we find the distance between all visually. So, and also he implemented we use his algorithm to find the center of all vehicles on the image. And we take because when we use the correlation, it kind of finds the back of a vehicle or the front of a vehicle, and it's off-centered. So we pretty much find the smallest distance between where I found it and where our real center is. And we pick that real center in the correlation. You'll be able to see it when we show some runs. Then we set the new vehicle center to the closest visual center, and we update the size based on where we are on the actual image. Okay, here is pretty much a breakdown of how my correlation works. Here is the real image. Okay, here is the window that we have picked out of the image to search. Okay, and then here is our mask that we will be using to try and locate the vehicle. So we take this mask and we correlate it across this image until we find the image, and then as you can see here, we have a star where the actual vehicle is on the image. Okay, so, and also we have a problem with losing a vehicle. Maybe in one image we won't find the vehicle at all. We'll just lose it. This happens when, oh, sorry. This happens when the actual center of the vehicle is outside of the window that we are looking in. Okay, so we enter a mode of just, it's a search, pretty much a search mode where we just continue moving at the velocity that the car was moving that we had set, and we just continue looking for it as we just move on. Okay, the velocity is picked out. This is a brute force method of controlling the velocity. We pretty much have a weighted average of previous velocities and the current velocity, so that we don't just move too fast out of the total image. And that's it. This can be improved. We're actually trying to implement a common filter which will help with the constant velocity of the vehicle. So that will help. We continue using that velocity vector and just trying using the same mask that we had before, and just keep looking for the vehicle as we move on by frame. And we also increase the size of the window by 10% each frame. So that way, it get bigger and bigger, and we would hopefully catch the vehicle soon. All right. And here we have a couple of runs of how everything.
I think you have to click on it.
Works.
All right, so I'll run it through, and then we'll go frame by frame if there needs to be any. And the red window is the search window, and the blue window is the basic. See, and it runs off the. It takes flight. But what's interesting though is that it will continue to find it even after it goes behind the tree. The red X in the middle is the identified visually, and the blue star that's behind it is Brandon's correlation. So that as it moves here, this isn't the best example, but as it moves here, you start to lose it temporarily, and you can see the mask size changing. You see it loses it here, where the actual center is outside of the search box, and the blue is where his correlation was previously. So it starts to enter a linear mode where it just keeps moving in the same direction, and then it eventually picks it up again. See, the box gets bigger and bigger, and then when it reappears, it hops over to it. But unfortunately, here it decides it takes flight. We have a few other examples as well. This one, I think it goes kind of crazy, and it just starts picking random vehicles, and then goes to the parking lot. But the mask size is changing due to the average size of the vehicles in the area. I guess we'll go on. I think this is the one. This is our best run, I believe. And then it loses it behind the tree here, and then when it comes out the other side, it finds it again. The same vehicle, because he keeps the same mask. And then it goes into traffic here, and then I think it loses it at the once it goes behind this last tree, and then it loses it there. But it doesn't even fall for, like here there's multiple centers in there, and it finds the best one. And then even when this other vehicle goes through its search window, right here, there's a vehicle there, it doesn't, because of the correlation, it picks the same vehicle. So, and this is, now that we have a frequency mask, we're going to try doing dynamic thresholding, where the images, the vehicles in the back, have a smaller threshold in order to detect them a little better. Better, like Brandon said, the better performance without the visual centers, using some a smarter estimation of where it's going. As of now, we just kind of add it, just something to keep the mask moving in the right direction. But like you said, some Kalman filtering could make it actually predict where it's going to go and be a little more effective. And then for future research, we're hoping to use the color to maybe eliminate shadows and create a better correlation from the colors of the car. And the model rule based is kind of like the filtering and everything. So I'd like to thank everybody involved in the project.
Well, I hope you spell my name right.
Oh, sorry. It wasn't in the spell checker, so I. Sorry. Do you have some questions?
Is there any kind of improvements you can do to your correlation, your mass correlation, to stay tracking better and not have flying cars?
Yeah, that was the common filtering is supposed to help. Because right now we are searching what the vehicle was previously. So with the common filter, we would search where we expect it to be instead of staying in one spot. We would just try to move with it. So that would improve it.
You just hadn't implemented that?
No, we haven't. I'm actually working on that now. So we try to implement that.
And the weighting of the predicted motion is really, it was just arbitrary half and half. It definitely could use some tweaking to get what the best, because we also wanted to get some video from the other side in the gravel lot where traffic isn't as constant, it's not just on those roads specifically, and see how it tracks there. But there aren't any cars anymore.
Like a getaway car in a field.
Right. Have people cutting donuts in it to see what's going on. Any other questions?
As a detection question, do you have any performance evaluation, like the probability of detection?
No, we haven't actually manually gone through and for the paper we're gonna run some data and manually count actual cars, because another implementation that we haven't done is it's only tracking a single vehicle now. It's not hard to expand it to track all the vehicles, but as of now we just pick a random vehicle to start with and track it. So once we implement all of that, we should be able to test it by manually counting actual cars and seeing how well it detects those vehicles.
Another question is, have you converted the vehicle moving in the picture into the speed?
Not really. Like there's no transformation. Like it's just the speed is just how many pixels it moved in the previous frames. It's not actually like a true velocity through a, what do you call that, perspective transformation, right?